Question 4. How many sets of 5 paintings can a museum curator choose from a collection of 8 paintings? A very innocent looking question. Only question 4. I think this is horrible. It's what's called a pigeonhole problem and is probably one of the least favourite types of problems on these sorts of papers, on competition papers. What I've done to help is I've actually recorded 2 other videos. I've recorded a video about type 1 pigeonhole problems, and I've also created a video on type 2 pigeonhole problems. Now we're going to be looking at type 2 pigeonhole problems, and here is a worked example on my other video that talks about just 5 choices with 2 options. On this question, question 4, we've actually got 8 options. There are 8 paintings, and you can choose 5 of those paintings. So 8 paintings, 5 is a lot more complicated than the example I've given you. So in my other explanation. So if you need to, go back and watch that video first. On this MathsCount paper, there are actually 2 pigeonhole problems. There's one on question 4, and the other one is question 11. I like question 11. It's the type 1 problem. This, however, is the type 2, and I really don't like it. Let me do my best at explaining it for you, though. The curator has these 5 choices. That first choice can be any one of those paintings. So the curator, she has 8 choices. Once a painting's taken away, though, so for instance, this painting is A. Once that painting is taken away, she only has 7 choices left for the second painting she chooses. For the third painting, she only has 6, and then 5, and then 4. So these are the options she's got. By the time she gets to the 5th painting, there are only 4 to choose from because she's already chosen 3 of them. It could be any of these. Sorry, she's chosen 4 of them, and it could be any of these that she's chosen, but that will be what we've got. So step 1 is to calculate the total possible permutations. And that is these numbers multiplied together. And that indeed would be the total number multiplied together if changing these round wouldn't make a difference. Let me give you an example. If we put painting A, we pick painting A first. So your curator, she picked it first, then B, then C, then D, then E. So this is one of those possible permutations. So if you calculated that out, it's one of those possible permutations. However, if she picked B first and then A, C, D, and E, well, it would also be the same 5 paintings. It would also be the same 5 paintings. If she chose E, D, C, B, A, it is still a possible, it's still the same 5 paintings. So these are 3 of these total possible permutations, but they are the same choice. So we have to eliminate, we have to remove all of these repetitions, these duplicates. And we do that, pigeonhole principle says that we do that by taking, so step 2, we have the total permutations, and we divide it by the number of paintings in final collection. It's the factorial of that. The factorial, if we had 8 factorial, for instance, it would be 8 multiplied by 7 multiplied by 6 multiplied by 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. 3 factorial, for instance, would be 3 multiplied by 2 multiplied by 1, to give you a feel for it. And we actually need the number of paintings in the final collection. There are 5, 1, 2, 3, 4, 5 spaces. So we're looking at 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So let's write that out. Total permutations. I'm actually going to write it down here, just because I've got a bit more space. This here is total permutations. 8 multiplied by 7 multiplied by 6. This is total possible permutations. And we're going to divide it by factorial 5. 5 multiplied by 4. Now, I can divide to 1. I've got a 5 on the numerator, 5 on the denominator. 5 divided by 5 is 1. I've got a 4 here and a 4 here. They both divide to a 1. Well, it is just 1, so I can divide that to 1 anyway. Then I'm left with 8 multiplied by 7 multiplied by 6 on the numerator, and on the denominator, 3 multiplied by 2. But we know that 3 multiplied by 2 is 6. 6 divided by 6 is 1, which just leaves us 8 multiplied by 7. 8 multiplied by 7 is 56. So this is the answer. There are 56 unique ways of selecting 5 paintings from 8 paintings. And that unique word unique is 56 unique collections. 56 unique collections possible. Because a collection is a collection of those 5 paintings, and the combination A, B, C, D, E is exactly the same as the combination E, D, C, B, A. It is exactly the same as B, A, C, D, E. It is exactly the same 5 paintings, and therefore it's not this horrendously big number. Let me just, I know you wouldn't have a calculator in the actual paper, but let me just show you what that would look like. 8 multiplied by 7. We're down to 4, yeah. It would be 6,720. If we could have all of those permutations, for instance, if it was the digits of a combination lock where this has to happen first and then this has to happen second, it would give us 6720. As I say, if you wanted to work this out without the simplifying, you could make this into 6720, and then you could divide it by 20, what's that, 20, 60, 120. You could take 6720 and divide it by 120. Sorry, there, if you really wanted to, because I was putting myself on the spot here. Let's see if I can do it. Yes, this is actually 56. And you could simplify that down. You could divide by 2, you could divide by 3, you could divide by 6 to be able to work this out. So if you didn't do it by the simplifying and you actually saw this and just went, right, I can do this, I'm just going to multiply all those together, then this is valid. You just need to remember step 2 to be able to, and it's the factorial 5. It is this here, which is your 120. That's the thing you need to divide by. I hope that was helpful. As I say, my least favourite of all of these questions. I hope that was followable. If it's not, come back to me, ask me some more questions, and I will try again.